In this video series about the energy efficiency of heat pumps, today we're going to talk about the seasonal SEER and SCOP, SEER for cooling mode and SCOP for heating mode. In previous videos, we had already defined what the EER and COP were, which were instantaneous seasonal values, meaning at a specific moment, a snapshot of the machine operating under Eurovent conditions that were defined for the unit at full load. Today we're going to look at those seasonal values. In the next video, we'll look at a special case, which is the SPR, which is intended for air-to-water or water-to-water chillers operating in constant mode, which would be a process chiller. And in the last video, we'll look at the ETAs, the seasonal efficiencies, but referring to primary energies. These parameters refer to final energies, that is, energies directly consumed from the electrical panel, whereas the ETAs refer directly to generation, to how that final energy is produced. It's a much more interesting concept, and in the end, it will show that the heat pump has a very pronounced renewable character. My name is Jose Arboleda. I am the Training and Regulatory Manager at KEYTER. And to carry out this study, the first thing we're going to do is take a specification sheet for a heat pump. In this case, we're going to take a rooftop unit, and looking at its specifications, we quickly come across this concept of SEER, operating in cooling mode. This concept of SEER has a note, which is note 5, and you should always read it when you have a specification sheet, since it defines the environment in which these parameters will apply. It tells us that it is the seasonal energy efficiency ratio, or SER, and the seasonal coefficient of performance, SCOP, operating in heating mode, which we will look at later, calculated according to 14.825. This standard, 14.825, is what will define how we should calculate these two parameters, these two seasonal efficiencies. The definition of SEER, according to this standard, 14.825, tells us that it is the annual demand that the heat pump is subjected to in kilowatt hours, divided by the annual consumption of that heat pump to meet that demand. Really, if you look at it, it's an ER. It's an R that happens here. It's not the instantaneous R at a given moment, but rather an average over the whole year. For the COP, for the SCOP, it would be the same, only working in heating mode. To do these calculations, we would need to define two parameters or two environments to work in. First, the climate zones or climate intervals, which are really the outdoor temperature profiles, in which the heat pump will be operating. Because when we defined the ER, we were working under conditions or at full load, 35 degrees outside, whereas now we are going to encounter, now we'll see different temperatures to work with. So by defining these temperatures, which are different from the nominal ones, we will have scenarios to work in, and we also need to know how the heat pump operates at partial load. Since a heat pump at 25 degrees outside won't need 100% of its full load like it would at 35, but will actually have more than enough capacity to work at a partial load. What are those climate scenarios, those intervals? Well, there are several. The first one we find, all of them are defined by the 14.825 standard, would be for air-to-air units of less than 12 kilowatts operating in cooling mode. Here, based on the outdoor temperature, it is defined how many hours per year these outdoor temperatures occur. It's a histogram, and we see that not all the hours of the year are used, which are 8,740, I think, but rather only 29.7% of the hours are used. Of course, that's for operation in cooling mode. In heating mode, we find a slightly different scenario, since instead of a single histogram, we find three. Why? Because Europe has been divided into three climate zones for heating mode. We will find the colder zone, or the coldest zone, where we will define 6,446 hours of operation per year, approximately 73% of the total hours. The medium zone, 4,910 hours, 56%. And the warmest zone, 3,590 hours, approximately 41% of the hours in the year, where the heat pump will operate. So not only do we need to define our heat pump, but we also need to define our heat pump and where it will operate. In fact, that's one of the design parameters we work with at KEYTER. Where is the heat pump going to operate? It's not the same for it to work in a cold zone as in a warm zone. In fact, what we do with the heat pump is eco-design, and we make sure the heat pump is designed to operate in those environments. What are those environments we mentioned earlier? Well, they are defined by the 3 climate zones we see here, into which Europe is divided. These climate zones have taken the climate data from the cold zone, the city of Helsinki, the average zone, Strasbourg, and the warmer zone, Athens. Using those histograms, they have divided the territory into these 3 zones with different colors, as you can see there, and for each one they have created a histogram. Here we have another histogram for air-to-air units over 12 kilowatts operating in cooling mode, and this one, since it's in heating mode, also shows us the 3 scenarios. We have the colder, average, and warmer scenarios. And this would be for air-to-air units under 12 kilowatts, or for comfort air-to-water chillers over 12 kilowatts operating in heating mode. How are the partial load conditions of the heat pump defined? Well, for each of the systems, we're not going to look at all of them. We'll just look at one, for example, this one for air-to-air units. It defines 4 points and 4 partial load factors to work with. One will be at 100%, another with the unit operating at 74, 47, or 21. And where? And why? With that data? Well, they took a typical heat pump and had it operate against different outdoor temperatures. At full load, as expected, 100% with an outdoor temperature of 35 degrees Celsius, operating in cooling mode, which would be the standard conditions. For 30 degrees Celsius outdoors, they considered that the unit would operate at a 74% load, and for 25 degrees Celsius outdoors, at 47% of its load, and for 20 degrees Celsius outdoors in dry bulb conditions, obviously at 21% of the load. This, when shown in the histogram, looks like this. At that point, where we have 20 degrees Celsius outdoors, obviously the unit will operate for many hours, which is why we'll later see that the SEER and SCOP are higher than the R and COP, since the R and COP, the ER in this case, would be at 35 degrees outdoors. It operates for very few hours compared to all the hours it runs at partial load, where the unit is oversized, so it will perform much better. That's why the SER is higher than the ER, and the SCOP is higher than the COP. So, for 20 degrees outdoors, we're going to have these hours, approximately 225 hours, during which the unit will operate at 21% for 25 degrees. It will operate at 47% for approximately 180 hours per year. For 30 degrees outdoors, it will run at 74% of its load for about 50 hours per year. And for 35 degrees outdoors, that is, at full load, 100%, it will run just over 20 to 21 hours throughout the year. Always maintaining constant indoor conditions, which are 27 degrees Celsius dry bulb and approximately 19 degrees Celsius wet bulb, that is about 25 to 48 to 50% relative humidity. For heating mode, in this case, we are talking about air-to-air units of more than 12 kilowatts and comfort air-to-water chillers of less than 400 kilowatts operating in heating mode. We find both for colder climates as well as for temperate or warm climates, different set points. All of these are based on temperatures. For example, here at -7 degrees, 2 degrees, probably around here 7 degrees, and about 12 degrees of outdoor air temperature. And what are the points and load factors at which the heat pump will operate to define those partial loads. All right, if we go back to the data sheet, we see that this is the SEER for cooling mode. In this case, it would be 5.3. And then we have the SCOP, which also uses the same standard, number 5, meaning it refers to the same thing, the 14.825, but working in heating mode. And we see that, in this case, it would be 4. As I mentioned before, the SEER of 5.3 is higher than the ER of 3.25, and the SCOP of 4 is higher than the COP of 3.21. Why? Because the heat pump will operate at those temperature profiles for many more hours. At partial load and below the nominal conditions set by Eurovent, which means the unit is typically said to be running unloaded, it has enough power to handle it, so it will be working with plenty of capacity to spare. If we were working with an air-to-water chiller in this case, we would be dealing with the SEER. Both in cooling mode for the cooling-only version and the SEER in cooling mode for the reversible version, which do not necessarily have to be the same. In fact, in this case, 5 and 4.29 are similar, but the equipment itself is not exactly the same. And we will also encounter the SCOP for heating mode when the unit is reversible. Well, that is all for this video. In the next video, we will look at that special seasonal value, the SPR, for process chillers. Best regards.